So why study numbering systems? You may be just getting started and learning about PLCs for the very first time. Or you've been working around PLCs and programming them for years. Either way, it's beneficial to have a good understanding of numbering systems and data types. They are fundamental to any computer system, including PLCs. It is a digital code that the PLC runs on. You have probably heard the expression, it's all ones and zeros. That's because PLCs are digital controllers. Digital meaning information is expressed as a series of ones and zeros. A numbering system that consists of only ones and zeros is known as binary. PLCs handle all functions at a binary level. Each binary digit is known as a bit. It occupies 1 unit of PLC memory, and it can be in one of two states, 1 or 0. To represent quantities higher than 1, bits are grouped together into larger segments. A numbering system is required to interpret the value of these segments of ones and zeros. In most control systems, there is a point where humans interface with the PLC. This interface may be an operator control panel or a PC running the programming software. We need to translate numerical data from how the PLC sees it to how humans see it. For that reason, numeric data is often converted to something we are comfortable with, a decimal format. So that brings us to what are the different numbering systems we will cover. As just mentioned, there is decimal, which are pretty much just normal numbers to us. There are other numbering systems commonly used for PLCs, including binary, octal, hexadecimal, and binary coded decimal known as BCD. It is helpful when working with and programming PLCs to understand how numeric data is represented. Some instances where you might see different numbering systems in use are sometimes internal PLC data tables represent data in a binary format. Some PLCs use decimal numbering to represent addresses, while other PLCs use octal numbering for addresses. Many PLCs and connected devices display error codes in hexadecimal. Since we need to know numbering systems, let's get started. Numbers, as we understand them, appear before us as a row of symbols called digits. The value of a digit depends on its position in the row, with the least significant to the right and the most significant to the left. Since the position of a digit matters in this way, this is known as a positional numbering system. Each numbering system has a base. The base is the quantity of unique digits, including the digit 0, that represent numbers within a positional numbering system. As an example, we can consider the decimal system since it's the most familiar to us. There are 10 unique digits, and that is 0 through 9. So we can say the decimal system has a base of 10. If we are counting up beyond the digit 9, we have used up all the unique digits that are available, so a 1 is carried over and added to the position on the left. And another note about the base, working with PLCs, sometimes the base is referred to as the radix of a number. So we have a number, 2022. How do we know what numbering system it belongs to? A common way of expressing the base is a subscript, or let's call it a tiny number to the lower right. So this number is base 10, so it's a decimal number. We are used to seeing the decimal numbering system all day, every day, so we seldom mark it as base 10 in this way. But we will use the notation for this example so we have something to compare to when we look at other number bases. So if we have a positional numbering system and the base is 10, we can look at it like this. The place value of each position to the left is more significant by 10 times. Beginning at position 0, the place value is times 1, and then at position 1, the place value is 10 times that. It is times 10. At position 2, the place value is 10 times that again. It is times 100. And then times 1,000, and so on. Based on that, we can see that the relationship between a digit, its position, and the base of the number is digit times the base to the power of the position is the place value of the digit in that position. Knowing that, the value of each of the digits in 2022 is, for position 3, 2 times 10 to the power of 3 is 2,000. For position 2, 0 times 10 to the power of 2 is 0. For position 1, 2 times 10 to the power of 1 is 20. And for position 0, 2 times 10 to the power of 0 is 2. So if we take the place values for all the positions and add it all up, it's 2022. Okay, we already knew that 2022 means 2022, but this is a demonstration. This process will make more sense when we look at numbering systems with other bases. And we will get to the other numbering systems soon, but I just want to sum up the decimal system first. The decimal system, and we now know it as base 10. The digits for this system are 0 through 9. And in the diagram, there is a picture of the decimal number 2022 used in an instruction in a control logics PLC. It is an EQU instruction, and you will notice there is no notation in the instruction to identify it as a decimal number. And there rarely is, because decimal numbers are so common. And here's one more look at the place value for each position and how to extract the overall value of a number from that. But as far as decimal is concerned, you've seen enough of this. Let's look at binary numbers. The binary system, it is base 2. The digits for this system are 0 and 1. That's it. So when we count from 0 to 1, we have used up all the unique digits available. To count higher, a 1 is carried over and added to the position to the left. And that's it. Just ones and zeros. So we have a binary number, 10111101. And in the diagram there is a picture of the number used in an older Allen Bradley PLC 5 instruction. It is an EQU instruction. Below you see the number again with the notation subscript, a little 2 to the lower right. There is no notation in the instruction to identify it is a binary number. There's a reason for this. This image is from a particular type of PLC where addresses that start with the letter B are binary. So the addresses here, B30 and B31, are designated binary, and they display numbers as binary by default. Even without the notation, it's not hard to identify a binary number when you see it. All the ones and zeros are pretty obvious. So let's continue with the binary number 10111101. How do we interpret the value? Well, we know if this is base 2, then each position to the left is more significant by 2 times. Beginning at position 0, the positional value is times 1, And then at position 1, the positional value is twice that. It is times 2. At position 2, the positional value is twice that again. It is times 4. And then 8. And so on. Based on that, we know that this is still true, that the relationship between a digit, its position, and the base of the number is digit times the base to the power of the position. And that will get us the place value for each position. So now we know everything we need to convert to decimal. Knowing that the place value is the digit times the base to the power of the position, we can start at position 0, 1, 2, 3, 4, 5, 6, 7. For position 7, 1 times 2 to the power of 7. 2 to the 7 is 128, times 1 is 128. For position 6, 0 times 2 to the 6. 2 to the power of 6 is 64, times 0. For position 5, 1 times 2 to the power of 5. 2 to the 5 is 32, times 1 is 32. For position 4, 1 times 2 to the power of 4. 2 to the power of 4 is 16. Times 1 is 16. For position number 3, 1 times 2 to the power of 3. 2 to the 3 is 8. Times 1 is 8. For position 2, 1 times 2 to the power of 2. 2 to the power of 2 is 4. Times 1 is 4. Position 1, 0 times 2 to the power of 1. That'll be 2 times 0. And for position 0, 1 times 2 to the 0. 2 to the 0 is 1. That place value is 1. We add the place values together, and we get 189 at base 10. And now we know what the number is worth. What about converting from decimal to other number systems? Beginning with the decimal number, the one you want to convert, you will divide by the base of the number system you are converting to. When you perform the division, you get two numbers, the quotient and the remainder. The remainder you will record as the first digit to the very right of the converted number. That would make it the least significant digit. The quotient you will divide again by the base of the number system you are converting to, yielding another quotient and remainder. Record the remainder again as the next digit to the left in the converted number. This would be the next most significant digit. The process is repeated until the conversion is complete. As an example of converting from decimal to binary, we will convert the decimal value 189. To begin, we divide 189 by the base of 2. We get 94 and a remainder of 1. So the remainder becomes our least significant digit, and we prepare to divide the quotient by 2. 94 divided by 2 is 47, with a remainder of 0. So 0 becomes the next digit to the left, and that is the next most significant digit. Divide 47 by 2, we get 23 and a remainder of 1. So 1 becomes the next digit. So you can see we just keep repeating this. 23 divided by 2 equals 11, remainder 1. 11 divided by 2 equals 5, remainder 1. 5 divided by 2 equals 2, remainder 1. 2 divided by 2 equals 1, remainder 0. And 1 divided by 2 equals 0 with remainder 1. And that is our final digit. So this is our solution. 189 in decimal equals 10111101 in binary. Moving on to the octal system. The octal system is base 8. The digits for this system are 0 through 7. So when we count up to 7, we have used up all the unique digits available. To count higher, a 1 is carried over and added to the position on the left. Let's look at an octal number, 275. In the diagram, there is a picture of the number used in a ControlLogix PLC instruction. It is an EQU instruction. Below you see the number again, with the notation subscript, a little 8 to the lower right. In the instruction, you see a prefix of 8 and the pound sign ahead of the number. This is a common way of identifying numbering systems in PLCs, with the number of the base ahead of this hashtag. To convert octal to decimal, using the digit times the base to the power of position, you will find the place values. Add up the place values, and you will have the decimal value of the number. In this example, octal 275 is equal to 189 in decimal. To convert from decimal to octal, it is the same process we already discussed for binary. You will divide the decimal number that you want to convert by the base of the number system you are converting to. So in this case, you will divide 189 by 8. The remainder becomes the least significant digit of the converted number. Take the quotient and divide it by 8 again, and the remainder becomes the next most significant digit. Repeat the process until the resulting quotient is 0, and you will have the converted number. In this example, the decimal number 189 is converted to octal 275. For the hexadecimal system, the base is 16. The digits for this system are 0 through 9 for the first 10 characters, and then letters from the alphabet A, B, C, D, E, and F to make up the last 6. That is to say, the value of A is 10, the value of B is 11, and so on until we reach F with a value of 15. So when we count up to F, then we have used up all the unique digits available. To count higher, a 1 is carried over and added to the position on the left. Let's look at hexadecimal number 21BA. In the diagram, there is a picture of the number used in a Mitsubishi PLC instruction. It is an equal instruction. Below you see the number again with the notation subscript, a little 16 to the lower right. In the instruction, you see a prefix of H ahead of the number. This is a way of identifying the type of numbering system. In Mitsubishi PLCs, if a numeric constant is in hexadecimal format, then there will be an H in front. Converting hexadecimal to decimal, using the digit times the base to the power of position, you will find the place values. Remember, if the digit is an alphabet character, you have to apply the hexadecimal value of the character. For example, B times 16 to the power of 1. B is 11. So that is 11 times 16 to get 176. And a times 16 to the power of 0, a is 10. So 10 times 1 is 10. Add up the place values, and you will have the decimal value of the number. In this example, hexadecimal 21BA is equal to 8,634 in decimal. To convert from decimal to hexadecimal, the process is similar to how we've converted binary and octal. You will divide the decimal number that you want to convert by the base of the number you are converting to. So in this case, you will divide 8,634 by 16. The remainder becomes the least significant digit of the converted number. If the remainder is higher than 9, remember, the characters for 10 to 15 are A, B, C, D, E, and F. For example, the remainder is 10, so we use the hexadecimal character A. Then we would divide 539 by 16, and we will get 33 with a remainder of 11. 11 is the character B in the hexadecimal system, so it becomes part of our converted number. Take the quotient, divide it by 16 again, and the remainder becomes the next most significant number. Repeat the process until the resulting quotient is 0, and you will have the converted number. In this example, the decimal number 8634 is converted to hexadecimal 21BA. So we have learned the numbering systems and how to convert between different bases to decimal and back. We do this to better understand what these numbering systems are and how they work, but converting them can actually be pretty easy. The easy way is with a calculator in programmer mode. If you start the calculator from the Windows Start menu, the calculator is available. The mode can be changed from standard to programmer. In this mode, there are displays for hexadecimal, decimal, octal, and binary. The blue bar to the left tells us that the calculator is working with decimal values at the moment. So numbers entered on the keypad are decimal values. We enter a decimal number, we get a simultaneous display of the number converted to hex, octal, and binary at the same time. Note 1,984 in decimal equals 7C0 in hex. We can change what base the calculator is working with by clicking hex, for example. Enter 7C0, and we convert it back to decimal 1,984. And that's the easy way. Binary coded decimal, known as BCD, is a system that is different from the positional numbering systems we've been looking at so far. BCD was designed to interact with field devices known as thumb switches and 7-segment displays, to input and display decimal numbers, but do it using a binary code. The key to this binary code is the ability to communicate decimal numbers from 0 to 9 with 4 binary digits. By the way, the short form for binary digits is bits. As we count up in binary, we see we can get all the way to 15 before we spill over into the 5th bit. Let's add ones in binary. Starting at 1, 2, 3, 4, 5, 6, 7, 8, 9, we pause at 1, 0, 0, 1. Then we can go 10, 11, 12, 13, 14, 15 is as high as we can go, because we go to 16, we spill over into the 5th bit. We can easily express 0 to 9 within 4 bits. 4 bits can actually store a value up to 15, but BCD only requires 0 through 9. So BCD works with these bits arranged in groups of 4. A group of 4 bits, by the way, is known as a nibble. Each decimal digit is handled as a separate nibble, and its value stored in the 4-bit binary code. An array of 4 nibbles can handle a 4-digit decimal number. When the thumb wheels, or 7-segment displays, are connected, the 4 inputs or outputs are wired for each decimal digit. Thumb wheels and 7-segment displays are kind of old-fashioned. You may not see so much on modern equipment, but there are applications where BCD is still used.